This lesson is for Chapter 6, Section 1. So everybody open up a new section of their notebook, and we'll get this one started. All right, so Chapter 6 starts us off with solving linear equations. There's 4 different ways that we're going to take a look at for doing this. We have the substitution method, the graphing method, the elimination, or in the past you've probably heard it called the combination method, or the 4th one, the Gaussian elimination method. But today we're only going to cover the first 2. So we'll be reviewing how to do this with substitution and graphing, and I'm hoping that you guys recognize this stuff. The substitution method. First, solve for one of the variables. Take that value that you get for that variable and sub it into the other equation everywhere you find that variable. Solve what you have. That's going to give you a numerical value for one of the variables in your system. Once you have that one numerical value, you're going to take that and put it in so that you can solve for the other variable in your system. So if we were going to solve this system of equations, okay, the first thing that I look for if I'm going to use substitution is I look for a line or an equation in my system that has a variable that's already by itself. Frankly, if I'm looking at a system and it does not have that situation, I use another method. So if you look at this top equation here, we can easily solve for x. I'm just going to move y to the other side. So if x is equal to y, I should be able to take y and put it in for any x in the other equation. So I'm going to put y in for this x. After solving, let me clean that up, I end up with a numerical answer for y. So that's half of what I need. So now I take the numerical answer for y and I put it into one of the equations for y. I'm just going to put it in the top one, and it doesn't matter whether you put it in the top one or the bottom one. Solving this one, x also ends up equaling 3. Now, you're not done at this point. You still have to state your solution. Solutions to these systems are coordinates. So you have to state your answer as a coordinate x, y. What we ended up finding by solving it here is something that we will be utilizing in the graphing technique more, but it's an intersection point of these 2 equations. Those are what we're looking for solutions. A story problem can be solved by substitution if you set up 2 equations based on the story problem. So in many cases, like in this particular one, we have a total of $25,000 being invested in 2 funds, paying 6.5% and 8.5% simple interest. The yearly interest is $2,000. How much is invested at each rate? So we have a couple of things going on here. We have an investment, and we have interest being earned on that investment. So if we set up an equation dealing with the money being invested, and we can set up a second one that involves the interest information, we're going to create a system. So we have 2 different percents. So let's let x be investment number 1. And then y is going to be the invested amount the second way. Okay, so the 2 of them together have to come to $25,000. So an easy equation comes from that looks like this. Now, our other information. The first investment that we're making is at 6.5%. So the second amount we know is going to be invested at 8.5%. Okay, so most of you guys understand percentages and investments and interest by now enough to know that whatever amount of money we invest in the first one, okay, so x, you're going to get 0.065 for all of x. So 0.065 times whatever x is, and if we add that to 0.085 times our y amount, we're going to come up with our total interest, which our problem tells us is $2,000. Okay, so take a look at those two equations that I wrote, and do you see where we had enough information in the story problem to build them? Now we can just use substitution, or frankly in the future, whatever method you want to solve these. Now the top one is an easy system to solve for one of the variables. So I went ahead and I solved for x. If you'd rather solve for y, it doesn't matter. But I ended up getting x is equal to 25,000 minus y. So this amount is the same as x. So now I'm going to come back to my second equation and put it in there. So now I have 0.065 times that equivalent for x, and the rest of the equation stays the same. Now I can solve. Okay, so using your calculator, doing a little math here. Combine your two y values. You can subtract 1625 from both sides. So we get 0.02y is equal to 375. Last step, divide by 0.02, and y is equal to 18,750. So you have one of your variables, you take that now and you put it into one of those original equations and you find x. So I'm going to put that y into the top one. So x plus 18,750 is equal to 25,000. Solving for x, we end up with 6,250. So your answer for this one is we had 6,250 at the 6.5%, and we ended up with 18,750 at 8.5%. Now, substitution can also be a way to solve systems where the equations in the system aren't necessarily linear. Okay, if you look at this system for checkpoint number 3, the top one is certainly a linear one, but the second one you have a squared term in it, so we actually have a parabola for our second figure. But if we're going to solve this system, we're still going to look for the intersection of where those two meet, which is a common point. So graphing will work on this one. We'll take a look at that method again here just in a little bit, but the substitution is going to work just fine as well. Now the top equation has a plain y in it. Okay, so I'm going to use that one just because it's already almost ready to substitute. So if I move the negative 2x to the other side, I get a 2x plus 5 to substitute in for y. So now I'm going to have x squared minus 2x plus 5. Be careful of that because it was a subtraction of your y. Keep your y, that 2x plus 5, contained into a parenthesis right now. We want to subtract the whole y, not just the first part of y. So now get rid of that parenthesis. Do some simplifying. So x squared is the only x squared term. Negative 2x and positive 3x are positive x. Bringing the 1 over from the right-hand side, I get minus 6. Now you're looking at a trinomial. Solving trinomials, the fastest way is to see if you can factor the thing. And we can factor this one into x plus 3 and x minus 2, which give us a couple of x values. There's an x, and there's an x. So all we need to do now is, one at a time, put those x values in and find their y partners. So my first x was negative 3. So I'm going to put that into the first equation. I'll get 6 plus y equals 5, or y equals negative 1. So my first solution is this ordered pair. Now put the other x value in and do the same thing. So my other solution, when I put 2 in, I got 9 out. So there's my other one. Now, once in a while, you're going to find that there is no solution to a system. If you think back, parallel lines. If it happens that the two equations that you're given end up being parallel, they're not going to cross if you were to graph them, and they won't have a common point at all. So a substitution method isn't going to result in an answer. Think about if we would have a graph that would look something like this. If we had a line that did this and a parabola that did this, okay, those two aren't going to intersect. So it might be a case where you come up with an undefined amount, or something that is unsolvable or undefined, like we have talked about in the past. And you're going to know then that that means that those two equations or whatever did not come together and give you a common point. So look at example number 4 in the book. I'm not going to do another one. You can look through example number 4 yourself. But notice they just go through the substitution methods that we've been reviewing. And it comes down to when they solved or tried to solve for x, it resulted in a quadratic formula with a negative root. And we know that those are undefined. You're going to get an imaginary thing for that. So at that point, you can quit because there aren't going to be any solutions for the problem. So if you ever come across a situation like that when you're solving, you didn't do anything wrong necessarily. It just happens that there isn't going to be a solution for the system. Now, the graphing method. When using the graphing method to solve, you are looking for the intersection of the points or intersection points of the graphs. All right. If two lines or a parabola and a line or two figures intersect, that spot that they intersect, that coordinate, fits or satisfied both functions or both equations. So they're going to be your answers or your solutions. You're going to be able to use the calculator to some extent, but I am expecting you to still be able to graph lines and parabolas without it. So you might need to review or ask a couple questions if you're not sure how to, get equations into y equals mx plus b form, or if you have forgotten how to graph a parabola, the ones with the x squared term in them. Okay, you guys are much more proficient than I am at the graphing calculator. So if you please look on page 428 at the graphical approach, play around with a couple of them, especially the ones that have logs in them, and see if you can find those intersection points. So for example, this one's the checkpoint number 5, and it's at the bottom of page 428. Go ahead and graph both of those. Our log functions, remember, are going to end up being a curve of some sort. And then the second line on here turns into y equals 2x plus 1. All right, so that one would have a y-intercept of 1 and the slope of 2 over 1. So that one's the easy one to graph. We are going to need probably the graphing calculator to come up with the top one in a timely fashion. So go ahead and punch those in and see if you come up with or can find an intersection point. Okay. Last thing that we're going to talk about today. Checkpoint number 6 is an example of how another word problem can be solved. In this particular word problem, we're dealing with a shoe company, and the shoe company is going to try to figure out where it's going to break even. All right, that's an important concept for a business because you don't want to lose money at something. You need to know, all right, what do we need to make or what do we need to sell in order to turn a profit? So that break even point is that threshold of losing money versus making money. So the example number 6 in your book is another one just like this. You can see that one yourself. So I took the checkpoint problem, which is very close to, but one number is different than the book one. So a shoe company invests $300,000 in equipment to produce a new line of athletic footwear. Each pair of shoes costs $12 to produce, and they sell for $60. How many pairs of shoes must the company sell to break even? All right, so we have two costs going on here, or two items going on here, and we're looking for when does cost equal revenue? All right, so when does the expense that you have end up equaling the money you bring in? Because that's the point where we break even. So our cost, for example, we know we're going to have to spend 300 grand to start up. And we also know that it's going to be $12 per shoe. So off to the side here, I'm just going to remind myself that X is shoes produced. So 300 grand plus 12 times every pair of shoes produced is my cost equation. Now the money brought in, the problem says that you're going to sell the shoes for 60 bucks a piece. So my revenue is $60 times X. Now we only want to have two variables going on in our system here so that we can solve. Well, if we're looking for the break-even point, remember we're looking for the spot where C is equal to R. So do a really quick substitution here and replace the R with a C. And that way we have a two variable system that can be solved. All right, looking at our problem up here, we have a substitution already to go. This variable C is already isolated. So wherever you see a C in the first equation, you can put 60x in. So do that substitution and solve. Move 12x to the other side. And then divide by 48. So we would end up having to sell 6,250 shoes to break even. That person, if they own that company, would know that anything beyond that is going to be their profit amount. Okay, examples start on page 431. Work your way through a number of these systems. You know, if you've got the substitution method down, it's not going to take a million of them before you can figure out whether or not you know what you're doing. So I'm going to leave that a little bit of a judgment up to you guys. But definitely spend some time making sure you can run the calculator. Don't pick easy ones that are all linear. Make sure you pick a couple where you have to graph a parabola. And then do some word problems, 59 through 63. Spend some time there trying to look at a story problem and set up these two equations like we just did on the shoe problem. And that one that we had with the investment stuff. Okay, all right, so assignment 431 to 433. Play with a bunch of them and we can go over a number of them in class on Friday.